Last video, ladies and gents, on plate margins. The first of which is a margin and the second of which isn't. That sounds weird, doesn't it? We'll get there when we get there. Okay, your final type of actual plate margin are called conservative margins. You can call them transform or strike slip, but vast majority of people call them conservative. The most famous one in the world is the San Andreas fault, which is why most maps and diagrams you will ever see about them are of the San Andreas. But there are others, definitely. So, divergent margins, the plates are moving away from each other. Convergent margins are moving towards each other. In this type of margin, the plates are moving past each other. Now, this is a really important thing at A-level. You can get away with it at GCSE, but A-level, we would rather you're a bit more precise. So, look at the first bullet point. Plates try to move laterally, that's kind of sideways, past each other, either in the same direction at different speeds or in different directions. Now let me make sense of that for you. If you had these two plates, ignore the word relative for a moment, I'm going to pick up on that. Let's just look at these arrows. If the Pacific plate is moving that way and the North American plate is moving that way, it is fairly obvious that you are going to get friction as these two lumps of solid rock try to move past each other. That's kind of obvious. But here's the thing. The word relative is actually quite important because actually the North American and Pacific plates are both moving in the same direction. But this one's going quite quickly and this one's hardly moving at all. Now, if you think about that logically, the end result is going to be exactly the same. If you're walking down the corridor in I was about to say in a crowded corridor. Okay, think back to normality, okay, before social distancing, before COVID-19, and think of a crowded corridor at Hewish. It doesn't matter whether you bump into someone going the other way or whether you're walking much faster than them and they're kind of dawdling along. If you brush into them, the end result is exactly the same, isn't it? Okay, and that is the truth of the San Andreas fault. The truth is that the North American plate is hardly moving and the Pacific plate is moving quite quickly. That is why you get lots of friction and lots of earthquakes along the San Andreas. So it means that that word, relative, is very, very important. It's their get out of jail free card for basically putting the arrows incorrectly. So, conservative margins, I know I'm really emphasising this point, but it's because people get it wrong. It doesn't matter whether the plates are moving past each other in the opposite direction or in the same direction at different speeds. You are still going to get earthquakes. All right, but there's no subduction here, so you're not going to get volcanoes. These are not volcanic at all, but you do get massive earthquakes. Now, I'm going to upset you. There are a few disaster movies about the San Andreas. I tend to avoid disaster movies on principle, really, just because the kind of the incorrect science just winds me up, really. I'm told that there is a movie about the San Andreas which involves a massive tsunami. No. The earthquakes that we get here are because the plates are moving past each other laterally. Remember that when we talked about convergent margins, which definitely are capable of producing tsunamis, what you need to produce a tsunami is a sudden sidewards or upward displacement of water. If the plates are not moving towards each other, you're not going to get that. Okay, so yes, earthquakes, definitely earthquakes at these. No tsunamis, no volcanoes. Doesn't mean they're safe. I mean, crikey, the earthquakes they get in California, etc., are huge. But fewer things that could try to kill you, I suppose. But please remember, if you can, the truth of the San Andreas is that the plates are moving in the same direction at different speeds, which, just to go right back to our first kind of margin that we talked about, which was divergent margins under the sea. And I said to you, if you really think about it, why on earth do you get earthquakes at divergent margins under the sea? Because where's the friction? If the two plates are moving away from each other, where's the source of friction? That doesn't make any sense at all. And the way I told you to think about the transform faults was like a mini version of the San Andreas. Well, the diagram that you're looking at in front of you is exactly what I was trying to get at. All right, so that's what I meant by that point. Okay, so hotspots. Hotspots are pretty much exactly what they sound like they would be. They are areas of the mantle which are much hotter than the rest of the mantle. So they are very much hot spots. We're learning them now because they have relevance to the module, but they do not necessarily happen at margins. They can be at margins, but they can be thousands of miles away from plate margins as well. They are wherever the area of mantle happens to be hotter. I know some of you are going to be sat there saying, why? Why are some bits of the mantle hotter? I need to know that. You don't need to know that for the A-level, actually. But if that's a bit of a sticking point for you, let me tell you. It's believed, bearing in mind we can't particularly go down and have a look, but it's believed that you get hotspots because of radioactivity. So some bits of the mantle have more radioactivity than others, and that makes them hotter. But truthfully, you don't need to worry. Now, here's the weird thing. We know that the plates move. We've talked about that on a number of occasions. Hotspots stay still. So, Hawaii, which is the hotspot that pretty much everybody talks about, Hawaii, the reason that you've got this chain of volcanoes is because the Pacific plate has been moving, and we just said in the San Andreas point that actually it's moving quite quickly. So the Pacific plate is moving, but the hotspot isn't, and that is why you get these long chains. How cool is that? But I'm going to hand over to someone who can explain it much better than me. Oh, once we get past the advert, obviously. Oh, there we are.
A hotspot is a localized source of high heat energy that sustains volcanism. It is not an isolated shallow magma reservoir beneath the crust, nor is it a pipe of magma that streams from the outer core. One theory holds that hotspots may begin as a blowtorch-like thermal perturbation in a zone between the liquid outer core and overlying mantle about 2,900 kilometers deep. The thermal plume allows solid, yet mobile mantle to rise very slowly and convect outward. Convection is the process by which heated material rises and cooler material sinks. Although magma may be generated as deep as 1,500 kilometers, individual blobs do not traverse the entire mantle. Let's zoom in to look at the onset of hotspot volcanism beneath a moving plate.
So we don't really need to worry about why they exist. This is our go.
Its heat is transferred to adjacent rock. This transfer continues to the base of the tectonic plate, where decreased pressure facilitates rock melting. The magma
So this is the hotspot, okay?
Rises through the plate in a network of cracks and shallow chambers and erupts on the surface.
Ta-da! Volcano.
Over hundreds of thousands of years, large volcanoes build on top of the plate. The weight of the volcanoes bends the plate downward. Volcanoes that spent their constructive life over the thermal plume slowly get rafted away.
So look, the plate moves, the hotspot stays still. This will gradually become dormant or extinct, and the active volcano is the one over the hotspot. But look, you're getting a chain of volcanoes.
This can explain why volcanoes can erupt again after centuries of quiescence. even after they have moved off the center of the hotspot. However, erosion greatly outpaces volcanism as eruptions wane, and the buoyant effect of the plume diminishes, allowing the volcano to subside.
Right, so they get eroded over time and they are then called seamounts. Not a crucial thing for your syllabus, it has to be said. You may want to rewatch that video a few times. Just remember, it's not essential for us to know why we get the hotspots. We just need to know that there are some parts of the mantle that are hotter. The hotspot stays still, the plate moves, and wherever is directly above the hotspot will be an active volcano. But as the plate keeps moving, the volcanoes kind of move away and they gradually become dormant. This diagram here sort of tries to give you a sense of which direction the Pacific plate is moving in and how old these islands are. Some people find that diagram quite useful. Oh, okay, sorry, we're going to have to do this. Let's just say none, thank you very much. And this, is the kind of effect you get, ladies and gents. So Kilauea on Hawaii is very famous. Can you tell I'm slightly obsessed by the lava? I just think it's amazing. Obviously terrifying up close, I'm sure.
Forceful impact I've ever had in my body in my life. That was just incredibly powerful and hot.
So you can see all that black is lava. And the reason the volcanic activity does not appear to be subsiding is because it is over a hotspot, so it's highly unlikely to. There are plenty. Now, we've mentioned the Icelandic hotspot before. Look, we've got this whole long mid-Atlantic ridge, and there's only one actual island. Well, that's because mid-ocean ridges, the mid-Atlantic ridge, it's not normal to have enough volcanic activity to produce an island. It just so happens that here, Iceland has been created by the combination of a divergent margin and a hotspot. So it is entirely possible to get hotspots at margins, but notice they're just kind of random. It's wherever there happens to be a hotter part of the mantle. This one's quite famous, the Yellowstone hotspot. The problem we have here, which we've already talked about with the San Andreas, is that the North American plate isn't really moving. You may have heard of the Yellowstone caldera, which everyone's a little bit scared about because the volume of magma that's now been accumulated is massive, and kind of at minimum it would take out sort of half of the US probably in terms of ash cloud. At worst, well, let's not even go there. And the reason that's happened is because the North American plate isn't really moving. So all of that magma from the hotspot is just building up and building up and building up. Hawaii, we've talked about. You may have heard of the Galapagos Islands, quite important for evolution and all sorts of things. They are created by a hotspot. So there's quite a few of them around the world. Just please remember, they can be at margins, but they are not necessarily at plate margins, which makes them a bit of an anomaly. This is just a little bit of a summary for you. So here's a list of all the margins and our sort of anomaly at the bottom of hotspots. And here's just some of the key words, some of the key things that you might want to sort of just jot down, some of the alternative names, etc., etc. And finally, the slide that I've talked about on a number of occasions. If I don't make perfect sense, I do really genuinely apologise for that. Ask Nick for his Q&A, but also these 4 hyperlinks might explain it differently, better, in a way that makes sense for your brain, whatever you need to do. Because as I've said, if you can get your head around the first couple of weeks of tectonics. What is plate tectonic theory? How do we know it? Why do plates move? The differences between my brain's not working. Oceanic and continental crust, all of your plate margins. If you can get your head around this first 2 weeks, the rest of the module is pretty straightforward, because it all sort of links from these key fundamental ideas. Okay, so see you in the next video next week. Thanks for your patience. Yeah, good luck.